Okay. You know, last time we discussed something that's Simon's algorithm. However, we didn't talk about the Simon's algorithm complexity figures. If you want to remember what Simon algorithm was, it was, in fact, at the output of the Simon's algorithm, you expect sequences. So let me just remind you what that was. So there was a hidden key S of m of length n bits. Okay. Okay. You expect to find this S such that for any x value on, for example, let's say in binary domain of n bits, then this function has this property that you have x and x XOR s, they give the same answer for any x. Okay? For any x, you have this functionality. And you're trying to figure out this s. What is this s? Okay? And we figured that in the worst case scenario, the classical approach is exponential time. Okay? From a complexity point of view. So therefore, we want, less complex quantum version. And that was the Simon's algorithm. And we realized that after the quantum circuit, given by Simon, when you do the measurement, you come up with a binary sequence whose dot product with this S is 0. Okay? That's the quantum counterpart of this algorithm provides. So therefore, we can use that information afterwards with a classical algorithm that would generate this S. However, of course, you cannot just use the quantum circuit only once to get S value. You have to do multiple times. You have to run this algorithm multiple times because it's all random. And there are, of course, to the n-1 possibilities here. When you do the dot product with S, it's going to give you 0. So therefore, I'm going to just walk through it again with an example, just to remind you what we learned about Simon's algorithm before. So let us consider n equals 5 bits, and this S, the key, is represented by S0, S1, S2, S3, and S4. Okay? And this is not 0. This is the trivial solution. Trivial solution is all zeros. And I assume that this S is not all zeros. Okay? I know this. This is just extra information given to me. And I assume that is not the case. Okay? Of course, there are, if you have this inequality, that means there are 2 to the 5 minus 1 possibilities. These are the remaining possibilities, if you will. Okay? And that gives you 31, right? Of course, not all of them has dot product with S0, so therefore, you can basically realize that there are 15 possibilities that's going to give you, 0, dot product of 0. So if you just run this circuit once with this F already implemented inside the algorithm, inside the quantum circuit, you will actually get the 5-bit sequence after the measurement. So let's suppose that the first try gives you 1, 0, 1, 0, 0 for the 5 bits. Okay? This basically means that S0 and S2, so this implies that S0 XOR S2 equals 0. Why? Because you can see that at the locations of S0 and S2 there are 1s. So that basically means that dot product of this and that should give you 0, and this boils down to this simple equation. Okay? And from that you also have to, you have got no idea about S1, S3, and S4. So you have to run the circuit one more time. Okay? So that is going to give you the second try. In the second try, let us suppose that we have 0, 0, 1, 0, 0. Okay? That gives us, of course, that S2 to be 0. Okay? So you resolve S2 by just looking at this output. Okay? Otherwise, the dot product would not be 0. Okay? Again, the constraint of the quantum Simon's algorithm or Simon's quantum circuit is that the dot product with the measurement result and the dot product of S must be 0. That is the basic principle that we keep in mind when we discover those S values. So again, since S2 is now found, which is 0, and we know that S0 and S2 are 0, okay, good. How about S1 and S4? Can't say anything about them at this point. So let's just give it the third try. Okay, in the third try, let us suppose we have 1, 1, 1, 1, 0. That gives us the following equality: S0 plus S1 XOR S2 XOR S3 equals 0. But we know that S0 and S2 are 0, so therefore this implies that S1 XOR S3 is 0. Okay? And from that, we've got no idea about S4, so therefore we have to give another try. Okay? So let us just give a fourth try, which is 0, 0, 1, 1, 1. That's the measurement result, by the way. And all of these measurement results happen with equal probability. Okay? Whatever the number of them. And 0, 0, 0 is also another possibility because the dot product of that and S gives you 0. So therefore, there are 16 different possibilities here that can come out. And each happens with equal probability, meaning that each one of these measurement results happen with 1/16th probability. 1 over 16. Okay, so that basically implies that we have S2 XOR S3 XOR S4 is 0. Okay? Okay, so now if you can see that if you assume all of them to be 0, then all these equations will be satisfied. However, we know that they're not all equal 0. S2 is 0, therefore S0 is 0. Okay? Because their sum, their XOR is 0. How about S1, S3? Well, they cannot be 0, 0. If they are 0, 0, you see, if they are 0, 0, then S2 is 0. If they are 0, 0, then S4 must be 0 too. And that's going to give all of them to be 0, which is not possible because of this inequality. Therefore, S3 and S1 must be 1. Okay? They must be 1 such that their XOR is 0. And S2 is 0, S3 is 1, and then S4 must be 1 as well, so that you get a 0 here. Okay? And finally, from here, we found that by just looking at these 4 tries. We found that S0 is 0, S1 is 1, S2 is 0, S3 is 1, and S4 is 1. By just running the algorithm, the Simon's algorithm 4 times, we actually get to find the S, the key, the hidden key of the circuit, okay, of the function. The main requirement here for these outputs to be independent of each other. Okay? If they're independent of each other, then you just need those 4 equations, because each one of them defines an equation here, and you require these equations to be independent of each other so that you can find out what S value is. So if you assume that you run the circuit, okay, run the circuit n plus capital N times. Okay? This actually means what you're looking for is to find out of these, because each one of them defines an equation. Because each one of them corresponds to a specific measurement output. And measurement output corresponds to a specific equation in defined binary domain. So out of these many equations, you want to find n minus 1 linearly linearly independent equations. Okay, because not all of these equations would be independent. Okay? For instance, look at this. This equation and this equation are independent. But if you think about the following equation, these two. If you take these two and XOR them, you get this one. So therefore, these two equations are independent, but they are dependent in terms of that one. Because this can be obtained by just XORing these two binary sequences, making them dependent on each other. Okay? So that's why we require n-1. Why n-1? Because we do not like 0, 0, 0, 0, 0. Okay? In fact, if you... It's not the reason. The reason is, if you have n-1 linearly independent equations, that means you can figure out n-1 of these s values. Since in this case n is 5, you're required to find 4 of them. Okay? If you know the 4 of them, you can figure out the other, okay? Because that's the remaining one from the last equation. That's why we require n-1 linearly independent equations. So therefore, what is the probability of this? Because now they're all equal probability, right? That is to say, each one of them happens with 1/2 raised to the power n-1 probability. So therefore, we actually have a decoding, successful decoding. Okay, successful. That's a probability of success. Okay, is greater than or equal to 1 minus 1 over 2 raised to the power n, the capital N. Okay, that's the extra number of queries, okay, that you're making to this circuit. So if n goes to infinity, that means this will go to 0. 1 minus 0 is 1, so your success probability is going to go to 1. If n is 0, that means 1 minus 1 is 0. Your success probability is greater than or equal to 0, but that is actually what you know, what you already know. That doesn't give us much to think about. So, apparently from this equation we know that as the number of queries increase, the success probability can be better bounded with a bigger number. Okay? So your success probability increases. Alright? So here's the procedure according to this. First we find an error bound based on n, how many extra queries you need, right? Then you have to figure out that n. For example, somebody can say probability of success, okay, cannot be smaller than 0.9. Okay, go ahead and find n. Find n. Or find minimum n, right? Minimum n that satisfies this requirement. Okay? For example, n equals 1 cannot satisfy that requirement because that's going to give you 1 minus 1/2, which is 1/2. How about 2? It's going to give you 175. How about 3? It's going to give you 187.5. So it's still not there. Okay? But if n equals 4, that's going to give you 15 over 16. Okay? And that is greater than 0.9. Okay? So for instance, and then you have to go ahead and run Simon's algorithm. Okay, how many times? N plus n times. So therefore, if whatever the n is, in this case, this n is given to you. That's the length of the key that the function is defined on. So therefore, n plus 4, for example, in this case, is more than sufficient to meet this requirement. Okay, and then you solve the equations for secret key S. Okay, which is, so this is linear time, right? This is linear. But how about this is second, third? Solve the linearly independent equations. Okay, linearly independent equations. This is around quadratic time, right? Overall, it's quadratic time. Of course, this is subject to this probability requirement. That's why people don't call it as quadratic time. They actually call it bounded error quadratic time. Error quadratic time. You know why? Because you still have, I mean, success probability is greater than 0.9, but it doesn't really eliminate the unsuccessful cases, which still has some non-zero probability. That's why people call bounded error, because you bound the error or you bound the success in the meantime. And that's why people would call it bounded error quadratic time for this particular algorithm. As you can see, the algorithm has two parts. One of them is the quantum part, which you have to run n plus capital N times, okay? As n increases, you can bound your success probability better, according to this formula. However, the unsuccessful probability of being unsuccessful is still there. It's non-zero probability. It goes to 0, but it never reaches to 0 unless n is infinite. Okay. So Simon's algorithm is a bounded error quadratic time, and the classical algorithm, if you recall, in the worst case was exponential time. So compare the complexities between the two. One is bounded error quadratic time. The other is exponential time in the worst case. Therefore, these two algorithms, like the classical and quantum part, combined together, making up the Simon's algorithm, is less complex compared to the classical version. I would like to talk about today Groover's algorithm, the search algorithm, Deutsch and Deutsch-Jozsa algorithms, where we only run the, we query the quantum circuit only once. These algorithms require us to query them multiple times. So you have to first define the search problem, and I want you to remind you the classical search algorithms. There are many, many of them. So the title is Groover's search algorithm. Okay. We have got cards. Let's suppose we have cards, and those cards have numbers on them, say, or maybe they are painted to different colors, but we don't know them because we close our eyes, and we are asked to figure out the white card. For example, 3 out of 4 has black color, the other has a white color on it, and you can't see them, okay, because they're in a, maybe a bag. And you figure out one at a time, you choose one of them, pick one, and then see whether you figured it out or not. So how many times we should try? How many times we should give a try to figure out the white card? Okay, for example, if this is white, okay, there is no specific order because you've got no idea which one is white. So therefore, you probably have to choose the first here, you fail, and then you choose the next one, you fail, and then you choose this one, you figured it out, okay? So how many times we have to give it a try? So let's just think about it, because I'm going to assume that one of them is white with the same probability. So for example, this one is white with 1/4 probability, this one is white with 1/4 probability, and similarly this one and that one, they're both white with the same probability, 1/4. Okay, in this case, white could be this one, and you try it in a given order. Let's suppose this is my order, 1, 2, 3. This is the guessing order, right? We try to guess with this first card, and then second card, and third card, and fourth card. So therefore, we start from the first, and there's a certain probability of finding it in the first try. That is 1/4. So therefore, if you give one try, and there's only 1/4 probability to figure it out in the first try. If you choose, somebody actually chosen the second index, this card with index 2 has chosen to be right, then there is this 2 tries and 1/4 probability, because this is also chosen with 1/4 probability. But you have to give 2 tries to figure this one out. Okay, first this one and then this one. How about third one? You have to give 3 tries to figure out this to be white, and that is also chosen with 1/4 probability to be white. Okay? And finally, the last one, I was going to write 4 here, but we don't need to. Because once you've chosen, this one is not white, this one is not right, and this is not white, then you definitely know the last one must be white, because that is the last card that you have not chosen. That's why it's sufficient to try 3 cards before making sure that the 4th card is a white. Okay, so that is the average. This is the average number of tries, right? Average number of tries. And if you do this calculation, it's going to give you 2.25. Okay? So let me give you the general version of this. You can see in the general version, if you got n cards, okay, n cards, okay, then you're going to have 1 over n, right? Let's say m cards, not n, but m cards. 1 over n, and you have to sum all i's from 1 to m minus 1. Okay? So that is this, that. And last one is plus m minus 1 over n, right? Last one has to be m minus 1 over m. So that is the generalization, right? Of the problem with m cards. Okay? And that is the number of tries. Average number of tries. Average number of tries. Okay? And if you just do this math, quite simply, it's going to give you m minus 1 over m, m over 2 plus 1. And that is OM, right? So that is linear in M. Okay? It's linear in M because those M's cancel each other out, so it's going to be a function of M only, right? Linear time. So in this classical approach, we expect a linear time complexity, or query complexity, let's say, a linear time query complexity to figure out the right card. Okay? Now I'm going to talk about the quantum version, which as I'm going to assume that there's a function, again, binary function. Let me just give you an example with n 2 bits. Okay, so n equals 2 bits, meaning that we have f00 is, let's suppose, equals to 0, 1, and then equals to 1, 1. They're both zeros, and there's only one one input that f gives f1. Okay, and that input, suppose, is 1, 0. And the question is, how can we figure out this input? Okay, that gives us 1. The rest of them are zeros. We can extend it to, of course, here to any n or any m by the same rationale. M is, by the way, number of cards. Analogy is n equals 2 to the n, of course. Okay, and this is just an example function. Okay, that we're trying to figure out the input from. That gives us the output 1 for that particular input. The rest of the inputs are going to be zeros. Okay? So the question, how many function evaluations we need before we find this? Right? Okay, this is the exact same question that I just described in terms of cards. It's the same question. It's a function evaluation or picking up cards from a bag of cards. However, this is much more formal because now we define the function itself. And of course, the oracle or the gate that characterizes this function. Okay? That's the oracle or gate that characterizes this function. We don't know the inside, but we know what happens with this definition. Okay? This is the expression. So this is the circuit that corresponds to Groover's circuit. This is your input, 0, 0, that goes into the 2 different Hadamard gates in parallel. And we computed the corresponding, this red one, corresponding expression that is the combined state of these 3 qubits and this is given by this. This is for the first two qubits, and this is the last qubit. 1 over square root of 2 on the front coefficient of this qubit is carried along in the beginning of the expression. And then after the F gate, we got this green expression that describes what's happening. As you can see, we use this gate, this oracle definition, which you have y XOR f x0 x1 as to be the output of the last qubit. As you can see, what I've done, I didn't do anything, but just a copy of this functionality. Therefore, this actually stays the same. As you can see, it stays the same. But the last qubit now goes through this XOR operation, depending on what y is. If y is equal 0, you can see this is 0. Then you got this 0 XOR Fij, and we got 1 XOR Fij, and this minus sign is due to this minus sign. And finally, what I just said, that if Fij is 0, then this is going to be ket 0 minus ket 1. But if Fij is 1, then it's going to actually make it ket 1 minus ket 0. Since I want to keep this as a common term, what I do is, and also we know that one of the inputs only generates 1. The rest of them are all zeros. Therefore, I'm going to get that minus sign, okay? Instead of writing ket 1 minus ket 0, I'm going to write ket 0 minus 1 and put a minus sign in the coefficient, okay, as a coefficient. That coefficient is going to be embedded inside this sum. So whatever that Ij is giving me this 1, has got a coefficient minus 1 in this here. The rest of them are just plus. Coefficients are plus sign. Okay? So for this particular 2-bit example, okay, what I'm going to get if F10 is 1, okay, if this is the case, and this is my example, by the way, that's why I assume it to be correct. Then I'm going to have, this is generalized expression. I'm going to write a specific example, for this specific example, the output of the gate. I'm going to have 1/2 0, 0, plus 0, 1, minus 1, 0, because that's where I have F10 to be output to be 1. And I have got 1, 1, right? And this is tensored with, of course, 1 over square root of 2, 0, ket 0 minus ket 1. You see the ket 0 and ket 1 is a common term. Okay, I didn't want to change this. That's why I've got, instead of having ket 1 minus ket 0, I've got ket 0 minus ket 1. Okay? So therefore, we got this minus sign carried along inside this big sum here, and we got a minus sign here. Okay? So that is the final outcome that belongs to here. Okay. Now, if I measure, you can see that these two qubits right here on top, they are unentangled compared to the last qubit here. So therefore, these are unentangled. So whatever you measure for these two qubits, if you do the measurement, it's not going to change anything on the last qubit. However, when you look at the expression, if you measure them, you'll actually see with the same probability, this one, this one, this one, and this one. So it's not going to give you what you want. So that's why we need an extra modification here, so that the probability of seeing the input 1, 0 is going to be 1. Okay? Otherwise, it's going to create the same equal probability for every one of the possibilities, and it's not solving my problem, because what I'm trying to do is to search for this input and figure that out. Okay? So for this particular example, we're going to introduce this average mean gate or amplitude amplification gate. This should be a unitary transformation in order for this to be a valid quantum gate. Okay? So here is the definition of this gate. This is used to find the different sign component. So that's the main objective of this gate. So you have to amplify the probability that corresponds to this 1, 0 and reduce the probabilities that are on these unwanted components, because we know that they're not what we're looking for. So if a number, okay, if one of those values is, so this why they call it average mean gate, because it calculates the mean and then looks at the coefficients, okay, and compares them with the mean, okay, measures the distance, and then based on that distance, it moves those probability amplitudes in the corresponding direction. If we have Let's just forget about 1/2, then I'm going to consider later on. So let's just focus on this example with 1, 1, minus 1, minus 1, right? These are the coefficients that you see in front of these basis vectors, right? Plus 1, minus 1, plus 1, and plus 1. Or two-dimensional Hilbert space. So we calculate mean. What's mean? Mean is 1 plus 1 minus plus 1 over 4, which is 1/2, right? That's the mean of this vector. So what we do, as I just described it along the way, we actually look at the distance. For example, this one and this 1/2 has a distance 1/2, right? Since 1, the original value, is about the mean, what we do is we subtract this distance in the same distance. We use this distance, we subtract this distance from wherever the average is. So that means this is going to be now 0, because this is about the mean. So this is your mean, 1/2. This is where you are, 1. So the distance is 1/2. You subtract 1/2 from the mean to get 0, right? Because that's what our objective is. We're trying to make this entry to be 0. If amplitude is probability is 0, probability is 0. Okay, so that will never happen. Okay? So that means that you have the distance. Now the new value is mean minus the distance. Okay, that's what the gate is doing, by the way. So 1/2 minus 1/2 is 0. If we are able to do that with this new gate, then probability of this specific output, 0, 0, will go to 0. And that's what we want. Because we're looking for this input, 1, 0. Okay? Similarly, second and fourth, this one and that one, will go through the same transformation, so that their values will go to 0. And finally, let us just assume the same mathematical formulation or transformation for the minus sign. Let's see what happens with the minus sign. The minus sign and 1/2, the distance between them is 1/2 is minus 3 over 2. But in different direction. In other words, in positive direction, because minus sign is below, right? It's below, this is 1 minus 1, and this is 1/2. So this is 3 over 2. And you have to add 3 over 2 on top to, the same logic. Okay, the mathematical logic that we just used. So therefore we have 1/2, that's the mean value, and that's the distance, 3 over 2, but in the other direction gives you 2. Okay? So therefore, if this vector goes to this transformation, 1, 1, minus 1, 1, goes to this amplitude amplification or average gates, what you get at the output is 0, 0, 2, 0. Right? I'm going to actually show you that this gate is something implementable. Okay? But just bear with me that we got this some kind of a transformation that I just described, but if we have such a transformation, then this vector will be transformed into this, 0, 0, 2, 0. Instead of having 1, 1, minus 1, 1, we got now 0, 0, 2, 0. Okay? Which is good, because we already have 1/2 in the beginning, right? In the front side of this expression. Therefore, if you multiply this vector with 1/2, right? So if you just multiply 1, since it's a linear transformation, if you add a 1/2 in front, then you have a 1/2 in front here. That's going to give you 0, 0, 1, 0. That's perfect. That's what we're looking for. Because now the probability of seeing the right input, which was 1, 0, is going to appear with certainty at the output of the measurement. Okay? So, what is this A gate? Well, A gate is simply an orthogonal, actually orthonormal, to be a valid quantum gate, an orthonormal matrix, which is given by the following. I'm going to call it A2 because this is for 2 qubits, okay, 4 by 4, and this is given by the following matrix. Okay? If you just multiply this vector with this matrix, you will definitely find this one. Okay? So therefore, as you can see, this matrix with 1/2 in front, so sorry about that, there has to be 1/2 here. This gate here is an orthonormal gate, in fact. Okay? And if you just multiply, and this is implementable because it's unitary, so this can be implemented in quantum context. And if you multiply this vector here with this matrix, you will get what you want. Okay? And that's the desirable output, because this basically tells you that where you will get the correct input as what you're looking for. So you only need to run this circuit just once to figure out 1, 0. Okay? That was a good reason where I started with n equal 3 case. Okay? Because you just have this simple transformation matrix A that resulted in what you want. Unfortunately, for n larger than 2, like 3, 4, 5, a simple application of A will not result in what you want. I want you to consider this. For example, this is just a single evaluation of the function f. It's just a single evaluation. That means query complexity is 1. You just ask once, and you get what you want. In the same problem, in classical context, required on average 2.25 times. This 2.25 compared to only 1. Okay, you see there is an improvement. Okay, even with n equal 2 case. All right. However, for n larger than 2, for example, n equals 3, let's say. Okay, for n equals 3, I am going to have 1, 1, whatever that is. It's one of them will be minus 1, and then 1, right? And what you get at the front, 2 square root of 2, right? Because n equals 3. This is 1 over square root of 2 raised to the power 3 gives you 1 over 2 square root of 2. Okay, so that goes to an A gate. You can define the A gate similar to this matrix, but now it's going to be 8 by 8. Same format. When you have got 1 square root of 2 multiplied by 2 in front. But if you apply this gate, okay, let me just show you what happens. Complete the average. Average is going to turn out to be 1 over 2 square root of 2 multiplied by 6 over 8, right? So these ones here is going to go to 1/2, okay? And it's kind of easy to see because, you see, if you don't consider 2 over square root of 2's, this is going to be 3 over 4. So distance between 1 and 3 over 4 is just 1 over 4, right? And if you subtract 1 over 4 from here, you will see that it's 1/2. Okay? So I'm actually not considering these because they're going to be eliminated anyway. So you got this 1 transferred to 1/2, not 0. How about minus 1? Minus 1 is going to transfer to 10 over 4. Okay? 10 over 4. And apparently if you multiply this 10 over 4 with 1 over 2 square root of 2, it's not going to be 1. It was 1 in here. If you do the calculation, but it is not 1 in here. So therefore, this is not what you want. Okay? Although the probability of seeing 1, I mean all these undesired outcomes, goes to something smaller, and you amplify the probability of the desired input, coefficient, probability amplitude of the desired input is going up, okay, over the average. They're not still the ideal, okay? So therefore, what we do actually, we apply the same, we actually query this once again. In other words, you have to put the output here again to another Groover circuit. So you have to apply a Hadamard here, another Hadamard, and then the function has to be queried again, once again, and then another amplitude, amplification, or averaging value. In this case, what you're going to do, this is going to actually become smaller, okay, smaller, and this is going to get bigger. As you apply or query the same circuit, okay, more and more. In fact, as Groover's original paper showed, that if you apply this around square root of m, if you apply it again and again, how many times? Well, around squared on the order of square root of m. Okay, and m, as you know, equals 2 to the n. Okay, if you apply it around square root of m, then you actually get this to be very, very close, almost practically 0, and this to be almost equal to 1, with all these coefficients multiplied, of course. Okay? You have to also think about these coefficients here. Okay? So that is the paper shows. Okay? And would that be okay? Well, it's an improvement, because the original classical version was around O to the n, right? Linear time complexity. This is square root of n. Okay? Okay? If you, in terms of n, this is going to be 2 to the n. How about this? Well, it's going to be 2 to the n, right, over 2. It's still exponential, but you got some improvements, right, here. And unfortunately, Groover's search algorithm could not be done better. In other words, this is kind of the lower bound. You cannot do any type of search, better than Groover in any computing device. Okay, so therefore, this is just like a limitation, search limitation, the search complexity limitation. You cannot do better than this, unfortunately.